So in this part of the lab, we're going to look at the reflection of 3 parallel laser rays or beams off of a concave mirror and a convex mirror. So in this case, I have the concave mirror, so the curved part is the part that the rays are reflecting off of. I know it's hard to see this right now. I will shut off the lights in a second to show you this. But let me just sketch or trace the inside of that concave mirror. Do that first. Okay, now let me shut off the light. And you should see the 3 incoming rays and then the 3 reflected rays. The one in the middle is reflected right back on itself, and they're all intersecting at a single point, and that point at which they intersect is called the focal point of that concave mirror. So let's actually, I'm going to make dots again so I can trace them in later to actually follow the way that those rays are going, the incoming rays and the ones that are reflected. And then I'll turn the lights on again and connect them with a ruler so you can see this more clearly. So these are the incoming rays. And then this is the reflected ray right here. The one in the middle goes right back on itself. And this is another reflected ray. Okay, so let me turn the light back on. So again, these are the rays that were incoming into the mirror. Let's sketch those out. Okay, so all 3 of these were going in like this. And then the one in the middle reflected back on itself. So something like that. And then these 2 reflected at an angle like this, where they all intersected at one point, which again is the focal point of that concave mirror. Okay, so this is the direction of the reflected rays. They intersect at this point. Again, this is, I'll call it F for the focal point. And then the point at the center of the mirror is actually called the vertex. So the length, if we measure from the vertex to the focal point, that's going to be the focal length of that concave mirror. So in this case, if I measure that length in centimeters, it's around maybe 2.4. Yeah, 2.4 centimeters. So focal length is 2.4 centimeters. Okay, so that's for the concave mirror. Now let's do the same thing for the convex mirror, which is really just the other side of the mirror. So I'll set up my ray box again so I have 3 rays being emitted. But now instead of going to the concave side, I want to go to the convex side. So I want this side. Again, this is hard to see. I'll show you with the lights off in a second. Let me trace the mirror first. So I'm going to trace the convex side. And then I'll turn off the light so we can actually trace the incoming and reflected rays. You want to make sure that the ray in the middle bounces right back on itself. Actually, that looks pretty good. So I'll trace. Oh, you guys might not be able to see that. Let me see if I tilt it a little bit. You can kind of see the rays coming off. So they're being diverged away from the center. Okay, so let me sketch it. So incoming again. And then reflected, it's hard for you guys, I know, to see it in the video, but it'll be easier to see when I turn the lights back on. So something like that. Okay, so in this case, these are the incoming rays. So 3 of them again, coming in parallel. Okay, so these are all going in like this. The one in the center is coming right back on itself, so it's going back out like that. And these others are reflected off at these particular angles. So like that, and then like this. One thing to notice here is if you were to draw a line tangent to the mirror and then draw perpendicular, so something like this. I'm not going to do it because I don't want to busy up this picture too much, but if I draw perpendicular, then the angle of incidence should equal the angle of reflection again. Okay? Alright, so in this case, when we have the convex case, how do we figure out the focal length? How do we figure out the actual focal point? Well, if you look at this, it appears that the focal point starts from behind the mirror, right? So in order to find it, we have to actually extend these rays backwards behind the mirror. I'll dash it in here. And then same thing here. And where they intersect must be the focal point of that convex mirror. And the one in the middle goes right back on itself. So actually that's not bad. So this point right here, that would be the focal point of the convex mirror. And again, the center of the mirror is the vertex. So now I can measure this distance in centimeters. I'm getting around 2.7 centimeters. And that's going to be my focal length for the convex mirror. So 2.7 centimeters. Okay, so those are basically our experimental focal lengths. Right? We got 2.4 centimeters for the concave and 2.7 centimeters for the convex. Now the question is, how do we calculate the theoretical focal length? Well, to do that, we need to know the radius of curvature of the mirror itself. So the way to figure that out is the following. I'm going to sketch or trace, I keep saying sketch, really it's trace, the concave mirror. Okay, so that's the inside of the mirror. Then I'm going to draw two lines. We're assuming this is circular. I'm going to draw two lines that are tangent to that mirror, so that just touch the mirror at one point. Let's say it doesn't have to be anywhere special. Let's say right there. And then maybe another one right here. And now I'm going to draw perpendiculars from those tangent lines. So I'll come out at exactly 90 degrees. So something like this. And the same thing over here. Okay, and then where those lines cross, in theory, should be the center of the circle, right, which is the radius of curvature of the mirror itself. So what I would do is I would measure both of these in centimeters, and then really maybe take an average of the two, and we'll call that our radius of curvature. So for the concave mirror, let's see, this one is like 5.2. And this one, yeah, it's also about 5.2. So I guess in this case, it's going to be around 5.2. So the radius of curvature, R, for the concave is 5.2 centimeters. And it turns out theoretically that the theoretical focal length is half the radius of curvature of the mirror. Okay, so, and again, that will allow you to fill in the data tables in your lab handout, and then you can compute the theoretical focal length. So let me do the same thing for the convex, which really I'm just tracing the outside of the mirror now, so it'll probably be a slightly larger radius. And then you'll have all the values that you need for that part. So here I'm going to trace just the outside of this mirror. I'll draw two tangent lines. I'll draw perpendiculars. And then where they intersect should be the center of that circle. So right here, so for the convex, let's see, I'm getting about about 5.6 for this one. Yeah, also about 5.6. Okay, so again, for the convex, mirror, the R is around 5.6 centimeters. Okay, and now you can calculate the theoretical focal length for the convex mirror just by dividing that value by 2. All right, great. So now you should have all the data that you need for that particular table.